Last time we proved this lemma, which says that under the assumption that there exists a point of the manifold where for which the restricted exponential map is defined on the entire tangent space TPM, then we have that given an arbitrary point Q, there exists a minimizing geodesic segment joining P to Q, and M is metrically complete. And now we want to prove the Hopf-Reno theorem, which says that a connected Riemannian manifold is metrically complete if and only if it is geodesically complete. That is metrical completeness and geodesic completeness are equivalent. I want to recall the meaning of geodesically complete. This means that every maximal geodesic is defined on the real line R. Okay, let's prove that geodesically completeness implies, geodesic completeness implies metric completeness. This is a consequence of previous lemma. Why? Because if every maximal geodesic is defined on R, then if gamma V denotes the in geodesic having initial point P and initial velocity vector V, then this is defined on the entire real line R, and we know that this can be parameterized this way. And since V is arbitrary, this says that the right hand side makes sense for any vector of the form TV in TPM And since t varies in R, this means that this makes sense for every vector W makes sense for any W in TPM. So we can use the previous lemma and we get the metric completeness. Now we have to prove the converse. So suppose that M is metrically complete, but for the sake of contradiction, it is not geodesically complete. If M is not geodesically complete, then there exists unit speed geodesic gamma defined on an interval of this form here, which cannot be extended, so no extension exists on 0 b prime with b prime larger than b. We will prove that under this hypothesis we can actually find an extension of gamma, and we will reach this way a contradiction. So suppose that Ti is a sequence which is increasing and approaching B. We define Qi to be gamma Ti. Then we have that the length with respect to the metric G of gamma restricted to Ti Tj. This is absolute value of Tj minus Ti, because by hypothesis the geodesic gamma has a unit speed. This implies that the distance between Qi and Qj is not larger than this quantity. This is true because the distance is defined as the infimum over all piecewise curves joining P to Q, Qi to Qj. And Qi This is a Cauchy sequence because for I and j enough large, this number will be smaller than epsilon. M is complete, metrically complete. So this implies that there exists a subsequence. Now let's say we don't need a subsequence. I'm sorry, I made a mistake. Implies Qi converges to a point Q in M. Then let's take W as the uniformly delta normal neighborhood of Q, where delta of course is a positive number. Then we choose J large enough such that Pj is larger than B minus delta, and Qj equal gamma Tj belongs to W. So if you want, we can make a picture. So this is the image of gamma. This is Q. This is Qj. This is W. Then if we consider B delta Qj, which is, for example, let's use another color. This geodesic ball then we have that the fact that every unit speed geodesic starting at this point Qj exists at least for t in 0 delta So let's define a geodesic sigma such that sigma 0 is a Qj sigma prime at 0 is gamma prime Tj. That is this vector. And then we define gamma tilde on 0 Tj plus delta with values, of course, in M as follows. This is equal to gamma T if T is in 0B, and this is sigma T minus Tj if T belongs to Tj minus delta, Tj plus delta. Both curves are geodesic, and they have this property. If T is equal to Tj, gamma Tj coincide with sigma Tj minus Tj equal Qj, and gamma prime Tj, this is sigma prime at Tj minus Tj equal gamma prime Tj by construction. So we have two geodesics with the same, which pass by the same point with the same velocity vector. So by uniqueness, the definitions agree where they overlap. In other terms, gamma tilde T is an extension of gamma T, and the reason of this is that Tj plus delta is larger than B, because we chose Tj to be larger than B minus delta, and this is a contradiction because we define gamma T as a non-extendable geodesic. This theorem has the following consequences. The first one is the definition of completeness. You can use the following expression: a connected Riemannian manifold is complete if it is either geodesically complete or metrically complete. Previous theorem says that these two properties are equivalent. The other consequences are three corollaries. The first one says that if M is connected, if there exists P in M such that the exponential map at P is defined on all of ppm, then M is complete. The proof of this corollary is immediate. Just combine the lemma and the Hopf-Riemann theorem. By the lemma, you will have that the manifold is metrically complete, and by Hopf-Riemann theorem, you will have that is geodesically complete. So you can say that M is complete. The second corollary says that if M is complete, and connected, then any 2 points in M can be joined by minimizing geodesic segment. You can prove this, for example, arguing by contradiction. And the last corollary says that if M is compact, then every maximal geodesic is defined for all time. That is, the manifold is geodesically complete. How to prove this? If you want to prove this, you use the fact that on a compact metric space, a closed and bounded subset is compact. And you can use this fact to prove that any Cauchy sequence in N admits a convergent subsequence to prove that the manifold is metrically complete, and then you use the Hopf-Ferrino theorem to prove that it is geodesically, to get that is geodesically complete, that is this is true. Now we change topic and we talk about curvature, and in particular curvature tensor. Let's start from the following observation. If nabla bar is Euclidean connection, then if x, y, z are vector fields defined on an open subset of Rn, then we have that nabla bar x, nabla bar y, z minus nabla bar y, nabla bar x, z. This is equal to nabla bar x, y, z. If you want to prove this fact, you just use the fact that nabla bar x, nabla bar y, z, this is nabla bar x of y, z, k, delta k, and this is x, y acting on zk delta k, where I'm writing z in this form. In a similar way, you can prove that this is y, x, zk delta k, and their difference this is equal to nabla bar of z in the direction of the Lie bracket of x and y. We say that a Riemannian manifold is flat if it is locally isometric to Euclidean space, that is every point has a neighborhood which is isometric to an open set in Rn with the metric G bar, that is the Euclidean metric. This definition justifies another definition. Actually, flatness criterion. Precisely, we say that a connection nabla on a smooth manifold M satisfies the flatness criterion if this is true. For any x, y, z smooth vector fields on an open subset of M. Clearly, it follows from this definition that the following proposition is true. If mg is flat, then it's Levi-Civita connection satisfies the flatness criterion. This is true because this is clearly true for the Euclidean metric, and consequently it remains true for any manifold which is locally isometric to the Euclidean metric. Now we are ready to give definition of curvature tensor. This is a map R from Km times Km times Km with values in Km and it is defined by this formula. So it is immediate from the definition that this tensor measures the failure of the flatness criterion. It is possible to prove that R is a multilinear over C infinity M, and it defines a 1,3 tensor field on M. The proof that R is multilinear is just a computation. I leave the details to you. Instead, I want to say something about the second part of the statement. This statement is consequence of lem B6 contained in the appendix B of the textbook. Essentially, the second part of this lemma says that a map F from tau 1m times tau 1m times Km times Km with values in Km where you have k factors of this form and L factors of this form, is induced by a smooth k plus 1 L tensor field if and only if is multilinear over C infinity m. So if you want to prove this, just use the first part of this proposition and this lemma with k equals 0 and L equals 3. So, what is the consequence of this proposition? Is that for each pair x, y in Q of m, the map Rxy from Q of m into Q of m defined by this assignment is a smooth bundle endomorphism of Tm, which is called the curvature endomorphism determined by x and y. The tensor field R is called Riemann curvature endomorphism or the 1-3 curvature tensor if x1, x2, xn are local coordinates, then this tensor has the following local representation: Rijkl dxi tensor dxj tensor dxk tensor delta L. Where these functions are given by this formula: R delta I delta J delta K. This is Ri J K L delta L. You can prove that Rijkl are given by delta I gamma JKL minus delta J gamma IKL plus gamma JKM gamma IML minus gamma IKM gamma JML. Let me check if I copied correctly. Yes, where gamma denote the Christopher symbols. If you want to prove this formula, you have to expand this the left hand side using the definition of R. I want to present this proposition which says that if gamma is a smooth one parameter family of curves in M, then for every smooth vector field V along gamma, we have that this difference is equal to the value of the Riemann tensor with x equal delta S gamma, y delta T gamma, and z replaced by V. What are the consequences of this formula? This formula says that the 1,3 tensor, curvature tensor, measures also the failure of the commutativity of the second covariant derivatives. If this is 0, then the second order covariant derivative do not commute. I want to try to prove this formula. So for each st in j times I, we choose these are local coordinates. This implies that the family gamma can be written as a function having n components, which are functions of S and T. We can do this because this is a formula which holds locally. So we can work in a neighborhood of an arbitrary pair st in j times I. And vst, this is vj st delta j restricted to gamma st. The first step for proving this formula is to expand the left-hand side. So you use the formula for the covariant derivative along a curve of V. So this formula contains two kinds of summands. The first one contains the derivative of Vj, and the second one contains the covariant derivative of delta J. So we can write delta Vi delta T delta I plus Vi delta T delta I. So here I'm dropping St, gamma St, and I made a change of index. Then we want to compute ds dt. So I have to apply the formula for the covariant derivative again to this vector field. So this time we get four kind of summands. The first one involves the second order derivative of Vi. The second involves these derivatives times the covariant derivative of delta I. The third one the derivative of Vi multiplied by dt delta I, and the last one Vi times the second order covariant derivative of delta I. Maybe it's easier to write. Okay, now we have to compute this, and it's enough to interchange the role of S and T. And if we subtract the formula we get this way, we get Vi ds dt delta I minus dt ds delta I. So now we have to expand this term and prove that it coincides with this. Now, in order to do this, we define S to be delta S gamma, that is delta gamma k delta S delta k, T delta T gamma, that is delta gamma J delta T delta J. And we use the fact that delta I is extendable, so dt delta I, which appears here, can be written as nabla T delta I. This is the tangent vector to the curves with S constant. And it follows from this formula that this is delta gamma J delta T nabla delta J delta I. But it's not finished because we want the ds of dt delta I. So ds dt delta I, this is ds of what we found there. And we get 2 kinds of terms. This is equal to delta second gamma j delta s delta t nabla of delta I in the direction of delta j plus this term, and instead of writing ds of this vector field, I can write nabla capital S of this, because also this is extendable. This is a linear combination of delta k with delta k extendable, so it's extendable. And this is equal to this term, which remains unchanged, plus delta gamma j delta t. S is given by this formula. So by the linearity, we have that this function can be factored out. So this is the formula for this term. We need a formula for this summand, but this can be done just interchanging the role of SMT. If you subtract, you get that ds dt delta I minus dt ds delta I. This is delta gamma j delta t delta gamma k delta s times the difference of two terms similar to this one. But this is just this term. This is just R delta K delta J delta I, where I'm using the fact that this term it is the same, but this is 0 because this is 0. And that one is RST delta I by multilinearity of R, because delta gamma j delta t delta j is t, and delta gamma k delta s times delta k is s. Now we define another tensor related to the previous one. the Riemann curvature tensor this is a 0-4 tensor defined by this formula Rm equal R flat. So this means that you obtain Rm from R by lowering the last index. To lower the last index means that if x, y, dw are smooth vector fields defined on an open set of the manifold, then you take r, x, y, z, and you consider the inner product with w with respect to the metric, of course, and you call this Rm x, y, z, w. In local coordinates, we have that Rm is given by this formula. Where these functions are obtained by lowering the last index in Rijkm, that is considering this formula, where of course I'm using the Einstein convention. We saw a proposition expressing this as a function of the Christoffel symbols. You can immediately get a formula for Ijkl multiplying that expression in terms of Christoffel symbols by GLM. Let me check how much time I have. Okay, so what do we want to do now is to give the proof of the fact that the curvature tensor measures the failure of the flatness criterion. So the next goal is to prove this theorem. Riemannian manifold is flat if and only if its curvature tensor vanishes. In order to prove this theorem, I need this technical lemma, which says that if nabla is a connection satisfying the flatness criterion, then given a point P in M and V in TPM, there exists a parallel vector field V on a neighborhood of P such that the value of capital V at P is exactly V. I will try to prove the theorem. Instead, I will prove the lemma probably next time. This implication here is an immediate proof, because if a Riemannian manifold is flat, the curvature tensor, it is 0. So there is nothing to prove. So suppose that the curvature tensor is 0. This means that the Levi-Civita connection satisfies the flatness criterion. The beginning of the proof consists in proving that the metric on the manifold M admits a parallel orthonormal frame in a neighborhood of a point. So let's fix P in M and suppose that B1, P2, Pn is an orthonormal basis of TPM. We can use the lemma and get that there exist parallel vector fields E1, E2, En on a neighborhood U of this point such that EI restricted at P is BI. The parallel transport preserves inner products This implies that E1, E2, En is an orthonormal frame. And the symmetry of the Levi-Civita connection implies that this is a zero The conclusion is that E1, E2, En are commuting. And now we use a proposition A48 in the appendix A of the textbook, and get that there exist local coordinates y1, y2, yn on a possibly smaller neighborhood U of P, such that EI is equal to this. In this coordinate we have that Gij is delta ij implies the map defined by these coordinates is an isometry from a neighborhood of P and an open set of Rn. And this says that M is locally isometric to Rn G bar, that is M is flat. And this is the end of the proof. Let's stop here.